Thanks, Peter, for this great introduction, and thank you for inviting me today. I also want to thank my collaborators for this work. Some the ones listed in the abstracts are here. There are many more, so thank you, especially if you're in the audience. Today, I wanted to present some of my work on how to use atmospheric physics knowledge to guide machine learning applications for both climate, and I'll also touch a bit on weather. We now have an example, and this is a collaboration listed here with Meteoswiss. And so this is a really general question. How can we best combine machine learning and the physical knowledge we already have about the atmosphere? I'm going to apply it to the very specific case of improving how we model convection for climate models, but a lot of the methods I develop, I always try to make them general and mathematical enough so that we can apply them in other geoscientifical settings. So to briefly motivate my particular setting, atmospheric convection can broadly be defined as any atmospheric motion driven by air density differences. Here I'm showing atmospheric convection often lead to storms, and here I'm showing you a very intense storm in the North American monsoon. And I think what's very visible in this movie is that this storm is really effective at transporting dust vertically. But what also matters for climate is that it doesn't only transport dust, it also transports water, in particular water vapor and temperature. And so at this, but you can see that storm is only like 1-2 kilometers in scale. So it's quite small, but yet it's transporting tracers really effectively between the surface, the atmosphere, and space. And for that reason, we want to resolve the effect of convection, storms, and turbulent processes on the large-scale climate in our climate models. And while we would love clouds to look like this beautiful photo taken from the window of a plane, in climate models, we forced to make computational compromises, especially if we're going to run them for hundreds of years. And although there's been a lot of rapid progress, right now, most climate models that are run for 100, 200, 300 years have pretty coarse resolution, think 800 or 100 kilometers, even coarser sometimes. And that completely distorts this interaction between storms and climate, and that explains why for a given emission scenario, so if we assume we know how much humans are going to emit, the biggest uncertainty in our long-term climate projections come from cloud-related processes. So and most of it is linked to the subgrid. So that can be convection, that can be microphysics, etc. And now the positive, the good news is that at least for convection, especially for deep convection, our recent ability to run global simulation at the kilometric scale so that we can run models globally that have a grid spacing as fine as 1 to 3 kilometers, and that's enough to explicitly simulate deep convection, really reduce those biases. So you get much better precipitation statistics, you get better representation of extreme events, and so we can resolve this interaction between storms and climate better. But we don't have the resources to run them for hundreds of years. So we have those beautiful simulations, but we only have them for 1 or 2 years. So what can we do with them? Well, that's when machine learning comes in. They're a really nice source of high quality training data. And then machine learning, and here I'm describing it in the broadest sense, any algorithm that can learn a task from data without being explicitly programmed for that task, can learn to mimic this 1 kilometer scale convective processes. And then here I'm showing the main setting I'm going to use in this talk, but we've also, we've had a number of collaboration where we've also done it on global TAD resolving model directly, the movie I showed you earlier. But today I'm mostly going to use a super parameterized setting where you have a traditional climate model on the left, and in each grid cell you embed a storm resolving models, and then the role of the machine learning algorithm, and that machine learning algorithm can be a random forest, but it can be in neural networks. We really like neural networks in atmospheric science because there's nice analogy with dynamical systems, but also once they're trained, they're really fast because you just having a few dense matrix operations and nonlinear function, it goes extremely fast. So once trained, if you plug it back in the climate model, you can accelerate it up to 10 to 20 times. And so it looks a lot like a low resolution model, except it has the benefits of a it has most of the benefits of a high resolution model. So the storm and climate interaction is better resolved. So to make things more concrete, these neural networks are trying to mimic this effect of storm. They take large-scale climate variables as inputs, insolation, the full vertical profile of temperature, water vapor mass concentration, surface fluxes, and then they output how storms and fine-scale processes in general redistribute that temperature in the vertical, water vapor in the vertical, and we're also interested in radiative fluxes. And if you evaluate them, especially offline, they do extremely well. So this is an example from a recent paper that was led by Griffin Moores, a PhD student at UCI. I work with Mike Pritchard, is also second author on this paper. And you can see if you compare the truth on the top row, that's what we're trying to emulate, the superparameterized simulation, to the prediction of the neural network. You have to really squint to see any error. To first order, it looks very good. And I think this is just one of many applications. At this point, there's at least 5 groups that have been able to do that in different settings. I'm also, I'm always really impressed by the results in data-driven weather predictions. So Jonathan Wayne is, and co-authors, he's one of the person who's been leading a lot of that progress, but there's also a lot of exciting papers that have come out recently using graph neural networks, for example. Machine learning algorithms can do really well. They can fully emulate a weather model so well that they can make a prediction 1 month in advance here. That's really impressive. And it asks the really provocative questions. Can we eliminate physics entirely? And by that, can we stop explicitly representing physical processes in the models we use to make operational predictions? And I'm going to show you a few issues now to make the point that maybe for some meteorological applications like nowcasting, it's possible to make arguments that maybe we just want to do some pure machine learning. For climate applications, especially long-term problems that response to, I'm going to show you pretty subtle boundary conditions. We may not yet be at the stage where we want to do pure machine learning for 3 reasons: physical consistency, interpretability and trust, and failure to generalize. So I'm going to first show you the physical consistency problem. And I think one of the good ways to show that is to show how neural networks, if just implemented naively, without doing anything additional, will break conservation laws if that allows them to improve their performance and reduce the cost function. So if here at the top, I'm going to show the residual from the mass conservation, I'm going to show the full histogram, and at the bottom, energy conservation. It's most enthalpy here because we're working on convection, but you can think of it as a metric for energy. And if the neural network was perfectly conservative and we fed a sample, a batch, through the neural networks, the output of the conservation, you would get zero, like a residual close to 0. We would have a nice peak here, but in practice, neural networks will leak energy at a rate that's pretty high, typically much higher than the forcing that we typically get when we're interested in long-term climate change projection, which is of order 15 to 20 watts square per meter for. Again, I think a recurrent issue that many groups have is that if taken out of the box, except in very specific hybrid setting where everything is controlled, neural networks that are not well trained, if coupled back to the numerical model, will lead to instabilities. And so you shouldn't necessarily trust these models without having extensively benchmarked them and understood at least how they make their prediction, not necessarily how every single connection works, but at least have a good understanding of how they respond to the condition they're going to be exposed to when run coupled to those numerical models. Finally, they fail to generalize when exposed to out-of-distribution condition, which is a bit different from out-of-sample. So climate change is an example where we are going to be in out-of-distribution conditions for at least temperature and water-related variables like water vapor mass concentration. So if I take a bunch of several neural networks that were trained in a reference climate and I warm the climate by 4 Kelvin, if I don't do anything, a lot of those neural networks are going to fail, and that includes neural networks that have engineered to conserve mass and energy. And so in the 5 to 7 minutes I have left, I'm going to bring some elements of answer to the question: how can we design data-driven models of convection that are that remain data-driven but are still physically consistent? And that is linked to the broader question: how can we best combine machine learning and physical knowledge? And I'm going to try to be conscious of times and leave time for questions. So I'm going to jump forward a little bit. Here, I just want to say it's part of a broader field. Now, physics-guided machine learning is an entire field that thinks about how we can add physical structure to restrict the output of machine learning algorithm to physically plausible solution. And when I review that field, for the particular case of the atmosphere, I like to show how there's many different ways to impose physical structure. From the most stringent way, where you're just learning the parameter of a physical model, but you're kind of trapped in the box of the physical model, and you can only output what's in the domain of that structure, to fully flexible approach where that we've played with in our work, where you take a neural network and then you just add just a little bit of physics, maybe just you rescale inputs to make them more physically consistent. But what I want to show today, and I'm going to skip the rest, is this example, which is physically constraining machine learning algorithms, either via the cost function or loss function, or by changing the architecture. And I'm going to show two examples, one for climate modeling, what I just said, and then another example that I find pretty exciting for post-processing for meteorological applications. So taking a step back, the most common and also pretty easy way of physically constraining a neural network is to introduce what we call a weak constraint, and to just penalize neural networks softly when they are not physically consistent. And so a very straightforward way to do that is just to change your loss function and to introduce a penalty whenever your machine learning algorithm is not physically consistent. I want to emphasize that penalty can be you don't need to exactly represent physical loss here. You could represent them to a given degree of approximation, etc. So this is a very flexible approach. So here I'm giving the example of a naive regression that tries to minimize maximize performance by minimizing mean squared error. And all I'm doing here is I'm adding a term penalizing the machine learning algorithm when they violate physical laws. So for example, it can be the residual from conservation laws, and you can use any norm here depending on the properties you want to have. But that wasn't satisfying enough from a climate perspective, because when you do that, because of usually we optimize those neural networks using stochastic gradient descent, you'll never perfectly have a zero mass and conservation residual, so you'll always keep leaking mass and energy. So we thought of a way to enforce conservation laws to within machine precision, and we did that in a pretty general way in neural network architectures. So the idea is we start with the standard neural networks. Imagine we have P outputs and constraint. We only output P minus N outputs, and then the rest we calculate exactly using the constraint. So that assumes you have analytic or at least closed form constraint. And then so far, it's not very original. What's really original is we do that within the neural network. So code it using your favorite language, JAX, TensorFlow, PyTorch. It can be anything as long as it's differentiable. And then that way, when you optimize the neural network, those constraints are taken into account, and the final weights and biases you have depend on those constraints. And so we have a way in a climate modeling context to enforce mass, energy, radiation conservation to within machine precision. So now I'm going to show in 3 minutes how we can also do it in a meteorological application. And that's work that's led by Francesco Zanetta, who's an excellent PhD student. I'm lucky to work with. He's supervised by Daniele Nerini and also work with Mark Lineker. And the idea here was in the context of post-processing, can we enforce physical consistency? And in that case, we want to enforce the ideal gas law, and we want to enforce Clausius-Clapeyron approximately. So whatever version of saturation vapor pressure Meteor Swiss uses, which is close to the Titan equation. So we start from an unconstrained setting. So we have this neural network that can process temperature, dew point temperature, pressure, relative humidity, and mixing ratio near the surface. And then we use this idea of architecture constrained neural network. And so we only output temperature, dew point deficit, pressure, and then we use the ideal gas law in the most case, so a general case, and this closest-Clapeyron integral that's operationally used by Meteor-Swiss to stay consistent, to then output relative humidity and mixing ratio in a way that exactly enforce both Clausius-Clapeyron and the ideal gas law to within machine precision. And I think this will come soon. I'm going to guess the preprint will come in the next month or two. The results are pretty promising from many perspectives. I think the main message, and it's kind of similar to what we had for the climate modeling case, is that you can improve physical consistency. So this is showing the residual from the Titan equation expressed from a relative humidity perspective as a function of relative humidity. You can see here there's a big residual. Loss constraint, you can reduce it, and architecture constraint, you can get the residual to 0 within machine precision. And you can do that, most importantly, without hurting optimization. So we don't lose performance. So if we look at the error, and so sorry, I'm just going to advance. The pink is the architecture constraint and the blue is the unconstraint. You have a full error bar here because there are 3 different cross-validation and 3 different random seeds. So you get 9 neural networks every time to make sure it works in a statistically consistent way. And you not only not compromise performance, you even slightly improve it for most variables. So that's really nice and promising. And I'm going to skip everything I had left and just go to the last slide, because I want to keep time for questions.
Yeah, we're not too bad on time in a sense. We also have a break after 3 talks. So yeah, but
okay, I'll just jump to the conclusion slide. And can you see the conclusion slide? Okay, great. So the message I want to deliver is optimistic, because it's really good news that the physical knowledge we've accumulated for the past 100 years it does not conflict in any way with the really nice computational improvements we're seeing in the past few years because of advancement in high performance computing and machine learning. And the idea is that you can use this physical knowledge to help machine learning algorithms be more efficient in terms of data and make predictions that lie within a domain that you trust is good. And you can do that without hurting optimization, as long as the physical knowledge you use is consistent with the data we have. So I showed that we can enforce physical constraint approximately using the loss function, exactly using the architecture, that it works for both climate and meteorological application. And then we have other paper, and for that, I'm going to just link my website, showing that you can also use physical knowledge to make the models more interpretable and trustworthy, and you can also use it to make them generalize better, which that's a really exciting result. In a climate change perspective, we've developed that climate invariant framework, which doesn't replace but complement transfer learning methods that are already available. So thank you so much. Don't hesitate to check out my website if you're interested. And do I have time for maybe 1 or 2 questions?